Hello, everybody. Welcome back to the SAS stage. I was going to come out here and go, does anybody remember Quantum Leap, the TV show? And then I thought, wait a second, they remade it. So now you're all up to date. You know what that is. Quantum Leap is where you travel in time. But of course, we don't need to talk about Quantum Leap TV shows. We already have it. Quantum is here. Quantum computing is arriving as we speak. So to talk about this, we're going to have the state of quantum, a panel consisting of Joe Fitzsimmons from Horizon Quantum and Faye Wattleton from EeroQ to talk about the state of the industry right now in quantum. And that's going to be moderated by our very own Flying Dutchman, Frederic Ladinois. Come on, Fred. Big round of applause, everybody.
Quantum Leap, I don't think I ever saw that. We've done these sessions at Disrupt for a couple of years now, where we kind of checked in with the quantum computing industry, and it always seems like, yeah, we're still 5 years out from something useful. So I always enjoy these sessions because it always feels like we're inching towards something that's inevitable. But before we get to talk about the current state, I want to talk about the two of you. What the hell possessed you to co-found a quantum? If I think of something that's difficult, quantum is definitely at the top of that. What possessed you to co-found and found a quantum startup? Yeah. Joe, you want to take that?
Sure. I mean, for me, this was a fairly easy choice. When I started out in my career, I've been working on quantum computing for nearly 20 years at this point. But when I was deciding what to do in university, I ended up taking theoretical physics, but I took it because I wanted to keep up maths and computer science and physics. But then when it came time to do a PhD, I really wanted to work on a kind of advanced technology. I thought it would be really cool to be part of a technological revolution of some kind. And I figured I need to get a PhD for people to let me work on this kind of thing, and I thought quantum computing would be the best thing. Now, it turns out that probably I was wrong on both counts, but you definitely don't need a PhD. But you know, I got into the area, worked for a long time as a professor, but really came to a point where I had written a lot of research papers, and I felt like the center of gravity was shifting from academia to industry, and that the real advances were going to happen in industry. And to be honest, I don't really trust anyone else to determine the direction, so I thought I better jump out and try and do it myself. So I raised a seed round, some of my group members came out with me, and we've been up and going for about 4.5 years at this point.
Yeah. Faye, your background is in many things, but not in quantum computing or theoretical physics or anything like that. What made you decide to get into?
Well, I was invited by my two co-founders, Nick Farina and Johannes Polonen, to join them in this adventure. And from the very beginning, the company, in the development at Michigan State University, felt that there needed to be someone on the team that had a broader perspective on the science that was being developed and the ambition that was part of founding EeroQ. It didn't seem so, I suppose, because I'm not a physicist, I'm not a mathematician, I'm just an ordinary citizen who has worked in the world of difficult ethical challenges. My background and my great notoriety is as the leader of the Planned Parenthood movement, but that came upon a foundation of nursing and health sciences that gave me a sense of what this journey might be and what we really were confronting in terms of the ethical challenges that science of this proportion would bring. My mother was a minister, and she was convinced that if she prayed enough and preached enough, people would follow certain strict practices in their conduct. And I guess I sort of have that leaning as well, that if we come together as a broad community of multidisciplinary players, that we can find a way of consensus that enables us to handle this technology in a responsible way that affects the lives of everyone in the world. It really has that potential.
Sure, sure. Now, just to get this out of the way right now, to just set the level, what's the state of quantum right now? Can I do something useful with a quantum computer at this point?
So I think it's really important to be clear on this point, that we have not yet reached the point where quantum computing is useful for solving hard computational problems. It's a major milestone for the field. There's a lot of noise about what's useful means and so on, and maybe it means press releases, maybe it means education. But if you mean solving hard computational problems that you could not solve on a conventional computer, we haven't yet crossed that threshold, except when that problem is simulating the quantum processor. We now have, I would say, 4 to 5 demonstrations that have come across industry and academia, where we've seen demonstrations of quantum processors that are convincingly hard to simulate, meaning that they can produce outputs that you can't easily predict on a conventional computer or predict their output distribution. So that's a prerequisite for advantage, but it's not advantage in and of itself. It doesn't solve a hard problem for you. But that puts us at a really interesting time, because now there's 2 paths forward. It used to be that the only path forward we had was to make better and better hardware until we got to a point where we could, where we would see real advantage. But now, because we've crossed this hard to simulate threshold, we're at a point where better insight into algorithms, better insight into how to use these systems can also lead to advantage with existing systems.
Which is what Horizon does to some degree.
Yes.
So it's in a good spot.
Convenient that.
But what is it going to take now to make that next leap? We've had this steady stream of advances over the years. Is that just going to continue until we get to advantage?
So one thing that has happened in quantum computing in the industry in particular is that there was a lot of focus on what were dubbed NISQ algorithms. And these are generally kind of variational algorithms which look a little bit like a neural network. So you guess what a circuit might look like, what a quantum program might look like, but you have a lot of the parameters undefined. And then you use a training process using stochastic gradient descent, often, to train these things just as you would a neural network. And you hope to get them to something that gives you a good output. So you're kind of learning the algorithm, learning the circuit that solves the problem. And you can do this for machine learning problems, variational classifiers, you can do it for optimization, and so on. But it's like throwing a neural network at an arbitrary problem. There's not really a good reason to believe it's going to work without an awful lot of training. And that can really erode any possible advantage. So I've never really thought that there was going to be much reason to believe that we'd see an advantage from that. But there was a lot of commercial interest in it because it could potentially lead to earlier revenue and so on.
Sure.
So there's lots of reasons to want it to work, but that's kind of power of wishful thinking. So now I think you see the field starting to get over that, to look beyond NISQ. And if you look, the last 18 months, there's been a lot of progress getting towards error-corrected systems, where you're actually squeezing out the errors and you're getting to real computers, to systems that look more like conventional computers, that are less error-prone, that can actually implement real algorithms.
Sure. What's the state there at EeroQ right now?
Well, the state of EeroQ is that we started from the scaling perspective, that we wanted to build a computer that would scale, and that is the opposite of the way that most approaches are taking. We felt that the use of tried and true materials in the semiconductor science would be appropriate for us to build the foundation on our CMOS level, and to move forward from the larger scale to putting more qubits on a chip, as opposed to starting with a small chip and building out. So we think that we started with an eye towards scalability, and the operative word was commercialization, but that wasn't why we started out. We started out saying, how can we build a useful chip with what we know and with tried and true methodologies and materials that will get us to where we need to be more quickly. And we believe that we are very much on the road to doing so. The question of how do you get involved in quantum, and I know that happens on everyone's mind, and There's probably a lot of you here in this audience that are questioning, why am I sitting here? Because I'm not a physicist, I'm not a mathematician, my background is in healthcare, and I say very proudly, I was on the board of Estee Lauder for 9 years and I still don't know how to make lipstick. But I can imagine what it means for someone to be able to be beautiful in the world and how that may change the world. And I think that's the potential here of quantum, that it will change the world as we know it in terms of our capacity to process information, to open new knowledge in the area that I come from, which is science, health science and medical science, for new drugs, for it's going to affect everyone on our planet. So I'm delighted to see this room, so many people here, because what you're saying is maybe we need to take a really hard look, and hopefully at the end of this we'll be saying, how can all of us get involved?
Sure. How many people here in the room have actually worked with a quantum computer yet? 1, 2, 3. All right, so the rest of you get started this afternoon then? It's about time. Yeah, there's plenty of them. You know, Amazon has them in the cloud, so it's not a problem. Joe, you brought up, or both of you kind of talked about the chip manufacturing, right? The state of like actually building a quantum processor right now. Feels like that's almost gotten, not easy, but that's almost a solved problem, just that core part, the quantum processor?
It depends on the technology. And actually, one of the interesting things that's happening in quantum computing at the moment is that you have quite a few different technologies that are all capable of universal quantum computing that are all starting to mature. So for a long time, superconducting qubits and trapped ions have been the leading candidates. Yep. But you also see purely photonic systems are certainly doing well at the moment, but you're also seeing neutral atoms. So companies like Atom and Pascal and QEra that are trapping large numbers of neutral atoms and being able to do some form of computation on them. And then at the same time, you've got silicon starting to mature, which had been for a long time stuck at 1 or 2 qubits. Now we're seeing 6, 12 qubits. So although it's far behind the 433 qubits that IBM have at the moment, it's still, it's coming up quite quickly. I should say that when I say a number of qubits, this is, counting the memory in a device, and it's like saying that you have a computer that has 433 bits of memory in total. So it can't really store a sentence. And so they're still really at a very primitive area, but if you look at the scaling at the moment, one thing that's interesting about quantum computing is that the scaling has gone from the number of qubits in a device doubling once every 5 years for the first 20 years of the history of quantum computing to a point where, since about 2016, they've started to double consistently about every 8 to 9 months. So you've gone from something that was much slower than Moore's law to something that's now, twice as fast as Moore's law.
I see you're shaking your head there.
Yeah, I think that sometimes when I hear these complex descriptions of quantum science development, and they are fascinating, and I'm dazzled by the physicists in my company and by colleagues on a panel, but I think that sometimes it's really harder to corral people than it is to corral the quantum science. And that is a major challenge for us, and it really is essential that this not be seen as a closed industry developing a science that is already upon us. The perception that somehow this is someone's experimental process in a lab someplace in perhaps Steve Jobs' garage. Those days are past, and this is a time when the revolution will not be televised. And that tells you a little bit about how old I am, that I talk about hearing of Gil Scott-Heron's very famous song, The Revolution Will Not Be Televised, because the revolution is about us. And look at what has happened to ChatGPT in the last 6 months, that many people have not heard about it, but now we hear about all of the technology that will impose on our daily lives. And that means that we all have an obligation in the science, along with the science, to think about the social implications. There are a lot of examples. Asilomar is one that had to do with gene therapy, and look at how CRISPR has emerged from that. So we can't really say that we don't have a good pathway to thinking about these issues and raising these issues in our laboratories, in our communities, in our churches, and in our schools, because it really does mean a tremendous challenge.
What are the social implications, though? Like, what are you referring to specifically?
Well, when I think about that, I think one about will it be held in the hands of a few as the major technology is held today at the expense and not of the benefit to those who do not have access. This is now largely a public-private, but largely a private developing science. The US government has, in my mind, put modest resources toward the development of this, even though there are security issues. So there is the problem of who's going to get the benefit of this, something that has the potential to really impact the rest of the entire world. Who will benefit? I'm sitting before you as a woman of color, very worried about what it means for the people from whom I've come. What does it mean in terms of the privacy violations that we all worry about every day when information is more highly powered than it is today, and in whose hands and who will decide what that will be. So there are a number of issues, mostly the issue of how do we begin the dialogue. That's the tough part. Are the anthropologists, are the psychologists looking at this from their perspective? Do we have to have the science upon us and the revolution is here before we say, wait a minute, let's talk about this and we better quickly regulate it? And I think we have time not to do a better job than we've done in the past.
Do you see an example, kind of a historical example in the world of tech where things went right or wrong that you can learn from? Maybe AI or...
Well, I'm not an expert on AI, but I certainly am in the world of health sciences, and that's why I referred to Asilomar. But I come out of a world where ethical violations are replete and have been replete, not only in healthcare that have resulted in the kind of regulatory procedures that all of us deal with every day, but in the area of reproductive health care and the violations of women's bodies in that regard is certainly prime examples of how we can't repeat the histories of the past. And we have a chance now to get ahead of it and let the AI debate and controversy inform the lateness of the day that we begin to have the conversation, to build a consensus before we resort to saying all of this must be regulated and the pushback that will certainly engender.
How do you think about that, Joe? Because you're building these systems too.
Well, I should say Faye is definitely far better placed than me to have an informed opinion on this. But what I would say is that when you think about what quantum computing is, it is essentially better computing. If you look back to the dawn of the kind of computer age, from the 1940s on, there's a lot of parallels in terms of the kinds of algorithms that are developed for classical computing and the kinds of algorithms that are developed for quantum computing. So you see cryptanalysis as one of the first applications, you see simulating physical systems, but then you also see various different kinds of mathematical methods, sorting and searching, different kinds of things like this, fast linear algebra, and Fourier methods, and so on. And even machine learning. Like you start to see the McCullough-Pitts paper on the artificial neurons from 1943. So you see this same kind of thing with quantum computing. So perhaps the history of conventional computing tells us a little bit about what the future of quantum computing will look like, and perhaps we can learn from past mistakes in that regard. But what I would also say is that we know some things are different in quantum computing than conventional computing. So, I mean, this is very esoteric, but there's a by now very well-known mathematical result that was proved about 2 years ago, showing that when viewed as a proof system, quantum systems are unimaginably more powerful than conventional. systems. So this was called MIP star equals RE, and it's just about complexity classes. But that is not what we expected the result would be. For all of the other complexity classes where we've gone from a classical version to a quantum version, we've seen that the results look similar. And this was a case where the result is completely different. So I think there's going to be results along the way that we're surprised by that I'm not sure we can foresee. So I agree that we should be thinking now about the issues that can arise, but I think we also need to be conscious of the fact that there are going to be issues that arise that we can't foresee now.
And I think that this does challenge us to have some imagination as to what is potentially the issues that might arise, and there's no problem with speculating ahead and projecting what there may be problems. Because, I mean, I think that, for instance, food insecurity is one of the planet's most challenging issues now, and with more data and information, is it possible that we really could address those challenges, those from fundamental human rights challenges for the quality of life for people on the planet. And I hope that we approach the science with that degree of humbleness and that degree of purpose. This is an opportunity for us to do this part of it differently at the same time that it takes nothing from our commitment to the science of to building these machines, but to the obligation to feel that I've got a responsibility to think about the implications and how this can be used for the betterment of humankind. And I mean, of course, climate change is one that is frequently raised and debated. In terms of just how much we'll learn about climate change. But I'd like to think that we could come up with better science with respect to the materials that we use and that we misuse for a better quality of life on the planet. Otherwise, why do this? Why not? Why would we have this kind of excitement and this investment in a science that is going to go no place but in the minds and the egos of the people developing it? I'd like to think that we can do better than that.
Unlike classical computing, though, quantum computing has almost become a nation-state issue. We've got different nations really trying to push ahead of others because the assumption is that there's much to be gained from not just breaking cryptography, but everything else that comes with it. That complicates all of this, though, doesn't it?
So, on the cryptography front, it's complicated. You're right. It's complicated in part by the fact that we should be able to move away from the cryptography that we use now, from RSA, from Diffie-Hellman, and move towards systems where we believe them to be difficult for quantum computing. I should say, I'm saying we believe. I have maybe a contrarian view on this, which is that I don't actually particularly believe them to be secure against quantum attack.
Okay, interesting.
But it's if you can do that, then the cryptanalysis isn't a massive problem. As long as you have the time to make the transition, and for all of the progress that's happening, and there is strong progress happening in the field, it's still going to take us time to get to a cryptographically relevant quantum computer. So I think that's a bit of a canard. I don't think that's really the main thing. Of course, you do get into things like how it may shake up economic status quo and so on, and like the economic benefit to be able to retain the capabilities in one country versus another and so on. I think that's more challenging than perhaps people making or thinking about policy necessarily realize, because quantum computing came from a field with not very many people in it for a long time. And they were spread out across the world, and everyone has papers together, everyone came up together, everyone knows each other. So there has been a long period of collaboration across countries. So actually, the current state of the art is pretty evenly dispersed globally, and putting it into silos is going to just slow progress, and not in a particularly beneficial way. Because if you're thinking about it from the point of view of, you're thinking about it in an adversarial way, and you think, well, I don't want my adversaries to have certain capabilities, so I'm going to withhold it from them now. Sure. That creates a circumstance where they are forced to develop it themselves, and you can never cut it off. So you just you just go to a world where everyone develops the capability independently. I'm not sure that's a better circumstance to be in.
I think there are people working on quantum all over the world, but to the point of how broadly based this is, I think it still is a pretty small, relatively small community. Would you agree, or do you think it's a big community of people? How do you feel about that?
It's definitely a small community, but there's many more people have come into it now. But in terms of it, like if you look across people leading efforts or something like that, they all came from a very small. If you look at the lead scientist for different programs or something like this, they all came from the same community, and that community was hundreds to small number of thousands of people.
And now it's expanding. It's exponentially.
Yes, but you have to keep in mind that the way it's expanding is at the less experienced level first, because it just takes time to gain experience.
Well, that's true. We've found that to be the case, which is one of the reasons why I'm saying that we have to take responsibility to start even before they're in the business of attacking these problems. In terms of just the science orientation to the development. And also I think that when we talk about history, in the context of history, the computer is not that old. We're not a century into this, folks. This has been at the beginning of the 20th century. The quantum scientists, if you've seen Oppenheimer, and my colleagues at EeroQ have certainly coached me dramatically before having seen that movie. People were saying that these were acts of God. We can't challenge that. And I've been wondering, what was Albert Einstein thinking? That sounded like my mother's ministry, my mother's preaching, talking about these were acts of God that we can't change, and this is the way it works. And just look at where we are, that we're defying all those acts of God in the science, or that were perceived as that. You look worried.
That's you, Joe, not me.
Yeah. I'm not quite sure what you're referring to about the acts of God. I was just.
Well, Albert Einstein felt that some of the quantum principles, the principles that on which we were built, were really a defiance of the way nature works.
This was very much rooted in him believing in a deterministic universe, where everything could be predicted forward from the known state of the current universe. And quantum mechanics, that's simply not true, or at least our perception of it.
We're a century away from that. That's my point. That how this has evolved and changed. Yes.
On a really practical note, though, you're touching upon something, is that the workforce in the quantum industry is limited right now, right? We had 3 people in the audience here who've actually worked with these machines or tried to write quantum algorithms. We're super early. The machines are coming, though. How do we scale that workforce? Because we can wait for, schools to start teaching this, but
it's a long journey.
It's definitely a long journey, but do we have that much time? Like, how do you scale up right now to get people?
Yeah, so what I would say is generally the way we approach this is usually in a kind of hierarchical way, where you need one very experienced person to be able to, give advice to a certain number of somewhat less experienced people and train people as you go. And that's, that works. It's a way of doing things. We have some people on our team who are at the more junior end. They're recent graduates. They're doing PhDs while working with us. So they're full-time employees, but they're spending half the time in the university, half the time with us. So we have to train up in that way. However, what I would say is that there's been a lot of recent progress in adjacent technologies, particularly in machine learning and the advent of large language models.
Yes, somebody said large language model. We've got all the sessions covered now.
It's like the theme for Disrupt this year.
It's weird.
It does open new possibilities in terms of how do you augment expertise? Like, how do you help people be more capable, be more productive than they would normally be at that level of experience? Can you give them the tools to make more progress more quickly? And I think there's some evidence that actually LLMs, for example, augmented with the current open scientific literature and so on do provide some tools for being able to do that.
Do you have enough?
I think that the conversation has to be made broader. It's the conversation is too narrow. The implications of this are global. All of us will be affected one way or another across disciplines, and the discussion, the consensus needs to be underway. And I think that to some degree, ChatGPT has accentuated what happens when something is perceived to happen very quickly that's been going on for a long time, and trying to grapple with the implications of it. And there's an opportunity here to perhaps bring more into the circle of dialogue of how we would regulate, how we would encourage good behavior, how we would create sanctions for bad behavior and expulsion for those who violate fundamental human rights, about which there are international frameworks for sanctions and for standards of conduct and the principles of conduct. So I'm personally very excited to be in this business, because you don't have to be in the lab as these geniuses are, and I'm dazzled all the time I hear them discuss it, to understand if you have a broad view of the world, or to imagine what your role might be in helping to bring this to fruition in a way that does not expand on the violations of the past technologies that we have all eschewed and hope that we don't repeat.
Nope. We only have a minute left, so just since you brought up ChatGPT, that was kind of this breakthrough moment for generative AI.
That just happened yesterday.
And that pretty much, it feels like it happened yesterday, but should we expect a similar moment in quantum computing where there'll just be this acceleration that we didn't expect?
I don't think so.
Okay.
So in terms of the way advantage is likely to proceed, from my perspective at least, is that we are first likely to see a narrow advantage, where it is really for one problem first. And it seems at this point overwhelmingly likely that that's likely to be a chemistry problem. However, quite soon after that, you would expect to see multiple problems.
Oh, we lost your mic. I got it for you. Had to happen sooner or later.
Yeah.
Yeah, why don't you take the handheld?
Oh, okay. So, sorry about that. So we're at this situation where there's likely to be a narrow advantage in chemistry first. That's likely to start broadening across multiple categories then following that. Long term, you expect to see really large advantages in a number of different areas that cut across things like finance and computer-aided engineering, computational fluid dynamics, computational geophysics, and so on, and machine learning, areas like this. But those are a little bit further off. So you're likely to see the narrow advantage first, and then the widening of that advantage.
All right.
So I would go back to my original profession, which is medicine and healthcare, when so many of the breakthroughs in those sciences were made supposedly by surprise, but that had gone forth, as Joe has described. So it's possible that there will be some breakthroughs that are not anticipated today that could come about and bring significant changes in quantum. Who knows? But there are examples of past developments. We certainly know that it won't be as long as we had expected. And when I became involved 5 years ago with EeroQ, it was still described as a laboratory experiment. And look at where we are today, 6 years later. That gives us perspective on how quickly things can happen, and breakthroughs occur all of the time. Medical breakthroughs are the example for which I could give out of the profession that trained my perspective on this.
All right, well, we're out of time, I'm afraid, but we'll do this again next year, and maybe we'll have had that moment then. Same place, same time. We'll meet again.
Thank
you.